Alright, chemistry students who are not as smart as me, right now we're doing the 2012 AP Chem free response question number 3. And I already messed up on this, so I drew all over the first equation, so I just copied it down on the piece of paper down here. It's the same, so don't worry about that. And in this question, we are told that a sample of CH3, CH2, NH2 is placed in an insulated container where it then decomposes into ethane and ammonia according to the reaction represented above, which is below, whatever. In letter A, we are asked using the data in this table to calculate the value in joules per mole K of the standard entropy change, or delta S, for the reaction at 298 K. 298 K just means the standard conditions, so you don't really need to worry too much about that. It doesn't play into the equation we're using at all. The equation we're using is just the reactants minus the products minus reactants, so you take 219.3 plus 192.8, which is for these two, which are the products. Go ahead and write those right there. And you subtract 284.9 joules per mole K, and that gives you approximately, or pretty much exactly, 127.2 joules per mole K. Notice it's joules, not kilojoules. That should matter later. It doesn't really matter now, but that is your answer. It matters in the delta G equation. In letter B, it asks us, using the data in the table below, to calculate the value in kilojoules, which is different, kilojoules per mole of the reaction at of the standard enthalpy change, delta H, for the reaction at 298 Kelvin. 298 Kelvin, again, doesn't matter. But in this, we're using a different equation than you'd probably be used to, because it's actually bonds broken minus bonds formed, which means we're subtracting the reactants minus the products. So what you do is you use the bond energies it gives you down here, and you find out how many bonds exist. So in this equation, we can see that there is 5 C to H's, 1 C to C bond, 1 C to N, and 2 N to H. And if you add up all those, that should be your bonds broken, which is approximately 3,488 kilojoules per mole. And then you do the same thing with your products, which is the bonds formed in the reaction. And you see there's one double bond C to C, and the double bond in the C to C is actually, or carbon on carbon, is actually greater than the single bond, because double bonds are stronger, so the energy it takes to form them is greater than the energy it takes to break a single bond. So there's 4 C to H, 1 C to C, and 3 N to H bonds, and if you add up all those, you get 3,439. So you subtract, again, the 3,488 minus the 3,439, and that gives you 49 kilojoules per mole in the reaction, and that is equivalent to your delta H, which you'll be using later, and that is the answer to letter B. Now, letter C asks us, I don't know if you guys can see that, scoot that up a bit. Based on your answer in part B, to predict whether the temperature of the contents of the insulated container will increase, decrease, or remain the same as the reaction proceeds, and then it says justify your prediction. So you pretty much have to look at what you solved in part B, and in part B, the delta H, since the delta H is positive, that means that the reaction is endothermic. That's something you just kind of need to know, and you need to realize that. If it's negative, it's going to be exothermic, but it's positive, so it's endothermic, and endothermic means temperature will get colder as heat is absorbed from the surroundings of the reaction. So that's pretty much what's going to happen, is that the temperature of the contents is going to decrease. It's going to get colder. And that's the answer to letter C, and we'll come back and do D, E, and F later.
Hello. We are doing questions number 3 of the 2012 AP Chem free response, letters D, E, and F. So, in this part, an experiment is carried out to measure the rate of the reaction, which is first order, which you might want to underline because it's very important. A 4.7 times 10 to the negative third mole sample of CH3, CH2, NH2 is placed in a previously evacuated 2-liter container at 773 Kelvin. After 20 minutes, the concentration of CH3, CH2, NH2 is found to be 3.6 times 10 to the negative fourth. So for D, we're calculating the rate constant for the reaction at 773 Kelvin. So first, we need to know the formula. Ln of AT equals negative KT plus ln of AO. Because first order reaction, that's the equation we use. So we know at the end the concentration of CH3, NH2 is found to be 3.6 times 10 to the negative 4th. So we plug that in for AT, and we're solving for K in this equation. So we have negative K, the temperature, which we had, time, I'm sorry. Time is 20 minutes plus ln, and then the concentration of the other one, we only got moles, so we have to divide it by the liters. So we do 4.7 times 10 to the negative 3rd divided by 2. And solving for K, we will get negative 7.929 equals negative K times 20 minus 6.05. Therefore, K equals 0.09395 over minutes. For question E, we are calculating the initial rate in molarity per minute of the reaction at 773 Kelvin. So for question E, we already got K, and we will have rate equals K times CH3, CH2, NH2. So, we know that K is 0.0940, and we had the molarity earlier, which was 4.7 times 10 to the negative 3rd divided by 2, and that equals 0.00235. So that'll come out to equal 0.000221, or 2.21 times 10 to the negative 4th molarity per minute, which is what they told us to solve for, right here. So for question F, we are, if 1 over CH3, CH2, NH2 is plotted versus time for this reaction, would the plot result in a straight line, or would it result in a curve? So since the reaction is first order, which it told us in the question, the graph of ln of A versus time is linear. Therefore, the graph of 1 over A is a curve. If the reaction was second order, then it would have been linear. Okay, thank you. That's all we have for you today.
Goodbye, chem students that are not as smart as us.